Okay, so thank you all for joining this presentation. Sorry about that small hiccup. Everyone loves Linux on the desktop, don't they? So today I'm going to be talking about Cloudstate, which is Lightbend's distributed state management system for serverless. It's a open source framework, but I think it's a lot more than that. We really want to move serverless to the next level. We see a lot of potential in serverless, and we don't think that that's been realized in the industry at the moment. So if we look at serverless today, let's call it serverless 1.0. We can see it supports stateless functions. Okay, so the platform itself, from the platform's point of view, there's nothing that it just invokes these functions, and the way, certainly when you talk to people about how you should develop serverless applications, your functions should be stateless. And stateless functions are great for handling events. If you need to handle something and then route the result somewhere else, it's great for that. For simple, as part of an ETL pipeline. So if you just need to transform an event to or something coming through an ETL pipeline, it's really great for that. Things that can be embarrassingly parallelized. But it's not great for handling requests that require state. And let's have a look at why that is. So here we see serverless deployment. We have a box of what the developer's responsibility is, and that's the code. And then the platform will hand that code a message in, and that code will handle it somehow and produce a message out. And this is usually in the form of HTTP requests, or it could be using some other protocol, like a messaging protocol or something. The actual mechanics of exactly what's going in and what's out, what protocols or whether it's messages or what is usually a platform concern. The code doesn't care so much. And that's one of the great things about serverless is that your code just follows, just focuses on the business logic. But what happens if we need state? Okay, so because most business applications, it's not good enough to simply have a hard-coded answer for every question. You want to answer based on some state that changes in response to various events. So currently today, if you want to handle state in a serverless, in function as a service in a serverless environment, you have to manage the database yourself. Now, it could be a cloud database, but you have to provision that database. Your code has to manage its connections to that database. You have to handle what happens if my code is responding slowly because of the database or because the code itself is slow. There's nothing that the platform, if for some reason your code is taking a while to respond, the platform has no way of knowing, well, is that because the code is slow and so should be scaled, or is that because the database is scaled? Because the platform has no idea that there's a database that the code's talking to. This is all opaque to the platform. And that's because in today's world, that the database is the developer's responsibility to manage how the code interacts with it. And so the question that we've asked at Lightbend is this the best we can do? Serverless, the whole idea behind serverless is that developers shouldn't have to think about deployments. They shouldn't have to think about servers, about what's connecting where, about where that stuff lives, about how it needs to be scaled, how it needs to respond to various events. Developers should just focus on their business logic, their ins and outs. And if they need to update state, the actual updating of the state, not how that state is managed. And so we at Lightbend, we don't think that this is the best that we can do. We think that a full serverless platform should manage state. So if you're having to manage a database, if you're having to manage connections to the database, we don't think that that's really serverless. It makes the server concerns developer concerns, such as where is my database? How do I connect to it? it's restricted to simple data access patterns. So we're saying that this isn't serverless. If your serverless function is talking to a database, then you're not really serverless. Your code may be sort of serverless, but you're hybrid with this. Also, I have to have this database managed on the side that is not serverless. So what if the platform could manage the state for us? Now, if the platform were managing the state, the developer's responsibility would just be the code. And as with Serverless 1.0, there's a message going in that the developer's code handles, and it produces a message going out. But if the platform was managing the state, then there would be an additional input to that, and that would be the state in that the platform was passing to the developer's code. And then there would be a state coming out, so updates to the state that the code emitted. And what exactly that looks like depends on what state model the developer is using. But the point is here, where that state lives, how it's managed, how it's replicated, how it's accessed, how it's scaled, is none of the developer's responsibility. It's entirely the platform's responsibility. And so we're calling this stateful serverless. You could say serverless 2.0, but or stateful serverless. And the idea behind stateful serverless is that the data developer should not think about how to connect to the database. They should just focus on their domain problem. So yes, I need to update some state. That's part of my domain problem. So when a user signs up for my application, part of my domain problem is that I need to store that user, store their details. I need to do that, but I shouldn't have to think about what does storing involve. Does it involve getting a database connection? What databases do I talk to, and so on? Because the platform is managing the state, it has deep state insights into how that data is used. Okay, it knows which state is being passed to the user function. It knows what's coming out, what's being updated. It's able to control consistency. It's able to make intelligent decisions about caching. So the platform can handle distribution. So should that state be replicated? Should it be sharded? Replication, caching. It can scale its state, decide, do I need to scale up my database? Do I need to scale up the number of nodes holding that state? And when we do this, obviously it allows the outsourcing of the complexity of state management. So there are many patterns in distributed computing that are quite hard to deploy and to set up. And we have a lot of experience of this because Akka, Lightband Akka implements these patterns, and we see people find it difficult to do them. But because the platform is doing the deployment, it can be made easy for the users. So patterns such as sharding, replication, and point-to-point messaging become trivial for the user to use. They don't need to set up clusters or worry about how things discover each other or split brains. That's all the platform's responsibility. They just use the patterns. So on Cloudstate, we have a number of different state models that we support that when you implement stateful code, you can choose from. So the first one that we support is event sourcing. So with event sourcing, your requests in are called commands. So you have a command that goes into your code and a reply to that. So the code, when it receives a command, can do some validation based on the current state and then do a reply based on the current state. To get that state, the platform passes it an event login. So before the command is received, it will replay all the events for the entity that is being talked to at the moment. And the code will then compute its state from that event log. And then in response to the command, it may emit some events out and update its state internally, which then those events get persisted and can be rehydrated next time the entity is activated. Another pattern we handle is for replication, serverless CRDTS. So CRDTs are conflict-free replicated data types. They allow reads and updates of a single entity to be done on many nodes concurrently with zero coordination. So even in the presence of partitions, you can do updates on your CRDTs and have no worries about whether those updates are going to conflict with anything else. So for these, you've got a message in and a message out, and as things get updated, you can have the state or the deltas of your entities passed in to be merged into your current state, and the states and deltas out. And the platform handles how all those states and deltas are replicated between all the nodes of your function that are running. And for P2P messaging, you can handle long-lived streams, and so be able to subscribe to messages on particular topics in a very scalable fashion, much more scalable than using a message broker, where subscriptions are fairly heavyweight. You don't want one subscription per connection, whereas when you use in-cluster distributed pub sub, like we support in Akka, we can have very scalable point-to-point messaging between nodes, whether that's to implement chat or push notifications or IoT notifications or whatever. So let me talk a little bit more about what Cloudstate is and how it's implemented. So it's built on Akka. So Akka is Lightbend's Active framework, which is a design for distributed systems to build scalable and resilient systems based on patterns that are decades old. So the features of Akka that we use, Akka cluster, obviously. So your stateful nodes all form a cluster. Cluster sharding to support sharding entities across your nodes, distributed data to support replication, distributed pub sub to support messages in and out. And it offers the best of Akka without needing to be on the JVM or to learn Akka. So it also uses gRPC to communicate with user code. So we use this gRPC protocol that's able to not just pass in the messages and commands that come in and go out, but also to pass in your event logs and to handle events out, and for CRDTs to handle your deltas and states. So the user code can be implemented in any language that supports gRPC, and we've provided support libraries for JavaScript, Java, Scala, GoSwift, C#, Python, and I believe there are more. So the user code, the services that the user code writes are implemented using gRPC itself. So the state function access your support HTTP so that you can convert those HTTP and REST interfaces. And we also support eventing through a message broker. It's built on, though not tied to Kubernetes. So we have an operator for Kubernetes that manages the deployment, and it leverages the sidecar pattern based on the presence of an annotation on your pods. And due to that, it's compatible with many deployment options. So Kubernetes deployments can be annotated, but not just Kubernetes deployments, Kubernetes jobs, Kubernetes stateful sets, anything that ends up being a pod can utilize this. OpenShift deploy configs, which are the OpenShift version of deployments. And we've also tested it with Knative services. So a wide range of deployment options there. And Cloudstate also has its own stateful service CRD that you can use. So just a brief overview of what a Cloudstate deployment looks like. So we can see here, we have an ingress, we have 3 pods and the user containers in those pods, and there's a distributed data store somewhere. So the user container is all the users concerned with, and the rest is the platform. So Cloudstate ensures that each pod has an Akka sidecar injected into it. And the ingress, when request comes in, talk to this Akka sidecar, which then talks to the user container via gRPC and also talks to the data store. The user container does not talk directly to the data state handed to it, the sidecar. And these sidecars also, they form a cluster, so they talk to each other so that they can do replication and sharding and point-to-point messaging. So if a request comes into the ingress, it's going to load balance that to one of the Akka sidecars. And in the case, let's say we're using sharding, that sidecar might say, well, this request is for an entity that's not on this node, but is on another node, so it'll forward it via Akka remoting to the pod that the entity lives on. It will talk to the data store to load the state for that node, and then pass the state and the request to the user container, which can reply and eventually send the response back to the ingress. So am I able to extend the time a little bit to do a demo?
Absolutely.
Okay. So I'm now going to give a demo. Now this demo is somewhat interactive. I've deployed it at this web address, csq&a.app. It's a question and answers application. You can see here, we can go here and click on a presentation, and I can ask a question. And right now it doesn't work because I've only deployed the front end web app for this. I have not deployed to the back end, which is going to be a Cloudstate service. So I can't ask any questions at the moment. So let's have a look at what it looks like to implement a Cloudstate service. Now today I'm going to be implementing in JavaScript. I mentioned that we support many different languages, but since JavaScript is something that most people know, it tends to be a least common denominator, I'm using JavaScript. So I've already set up a package.json, which is a fairly standard one. It's got a dependency on the Cloudstate library, and I've got some things set up here so that will allow me to do Docker builds, and I've got a Docker file here set up so that I can build my code into a container. It's a fairly standard Node.js, what happens when you do a Node.js deployment. The first really interesting thing is the protobuf file. So it defines our gRPC service that we're exposing to the outside world. Q&A service, we have two RPC methods, one for asking. This is for asking a question and also for voting on a question. So if you ask a question that's already been asked, it increments the votes for that question by 1. Returns empty. And here we have a watch request. So this gets all the current questions as well as streams out any updates to questions. So you can see it's a streamed response here. You can also see we have these HTTP annotations on here for HTTP transcoding. This is what allows us to talk to it from a web browser. This exposes it as a REST interface, and in the streamed response here will actually be exposed as event-sourced stream. So a very important thing to look at here before we move on is these requests, the ask request and watch request. Let's look at those messages. So you can see both ask request and watch request have a field called presentation, and that is annotated with this annotation saying that this is the entity key. So when Cloudstate receives an ask request or a watch request, it knows this schema, and it knows to look at the presentation field to work out which entity it's for. And this is how it knows where to route the what state to load, what state to pass to the user function, and where to route the questions. So on to actually implementing this. So the first thing that I'm going to do is require the Cloudstate CRDT support. And today we're implementing this using CRDT with conflict-free replicated data type. So we'll construct our entity, which we pass in the protobuf file as well as the fully qualified name of the service, of the gRPC service that we're implementing. And I'm going to set a default value for an entity. So when a message comes into a particular entity, if that entity hasn't yet been created or accessed, we're going to create a new OR map. So an OR map is the CRDT, it stands for Observed Removed Map, and it's basically a scalable map that can support concurrent updates, where the values are whatever keys you want. In our case, string will be the questions, and the keys will be the questions, and the values in the map will be another CRDT, which we'll see in a moment. So let's implement our ask function. We take in two parameters. The first is the ask request, and the second is a context, which allows us to interact with the state. So the first thing we do, does our current state, which is the OR map, does it have the question that's being asked? If it doesn't, then let's instantiate a new G counter for the question. So G counter is another CRDT. It's a simple counter, but it allows you can increment this counter on many nodes concurrently without any coordination, and it will ensure that all votes eventually get counted using the CRDT mechanism. Okay, and now once we've ensured that our counter is present for that question, we can then increment the count of the number of votes for that question by 1. And then we just return empty. So that's all we have to do for our ask request. Next thing we're going to implement is our watch request. So once again, watch takes the request and the context. And I'm going to implement some helper functions. So the first one is copy questions. It's going to copy the questions from our OR map into an object that will track which questions states we've already sent to allow us to diff it whenever there are updates. So then for each question in the map, we will update, we'll set the question in that map to the value and return the questions. So let's use that to copy the questions, and then we can return the questions. So this right now, when you invoke the watch request, will simply return their initial state and nothing else. We obviously want to, whenever somebody asks a new question or votes, we want to send that update down. So we're going to add a state change handler to handle that. So on state change, so anytime the CRDT changes, we will then, and again, we're going to implement another helper function. This is update and diff questions. So we passed in the questions object as well as the OR map, and we track what's been updated. So for each thing in the map, if either the question isn't in our questions already, or if the counter value has changed, then update both the updated map as well as the questions, and we can return the updated map. And so now we use that to get our updated map, and if updated is not empty, we will return the questions down the stream. And so now we've implemented our watch request. Just a couple more things to implement. We want to register those ask and watch command handlers. So this ask and watch here will match the name of the methods here, passing in these ask and watch functions. And then we start our entity. And now we're done with the coding. So I'm just going to npm run docker build push. So while that's running, the final thing we have to do is write a descriptor. So I've already written it here. I said that we support deployments and stateful sets and stuff like that, but Cloudstate also provides its own CRD if you want to use that. It's a stateful service named Q&A, and here's our user container, which is the Cloudstate Q&A image. So that now should be pushed, and now we can, I'll just show you the list of pods that are there now. As you can see, the front end is deployed, nothing else. So kube control apply -f Q&A.yaml. And now if we get pods, we should see our Q&A deployment there is now running. And of course, running this on one pod is not that interesting, and I don't have the load at the moment to be able to scale it up. So I'm going to manually scale that up to 6 replicas. And so we can see those are all starting now. And once they've joined the cluster, they'll report as being ready. So now if we go back to our application, let's see if it works. So I'll ask the question. Now it takes a little time for it to appear because the node that the question goes to and where we're subscribing for the updates to the questions might be different, and so it needs to be gossiped between those nodes and eventually come. So we can see I can vote for things, and we can see somebody else ask things, and so anyone else that wants to jump on here. When I've done this demo before, some people have decided to write scripts to update things very quickly, and very quickly it goes up to 10,000, showing how scalable this is. But yeah, that's an overview of how easy it is to write a stateful service using Cloudstate with a replicated pattern of things replicated across the cluster.